So now that we know what the natural log is and the E number is, we can actually apply that type of logarithm to some word problems. And so we're going to do a lot of that in 7.8, just apply natural logs and the E's to help us solve problems. So the first ones that we're going to look at, and if I were you, I'd take a screenshot of this box here. We're looking at exponential growth and decay. The equations are basically the same, okay? F of x or y equals a times e to the kt if it's growth. If it's decay, it's just negative. Otherwise, it's the same. So a is the initial value, kind of like p was in our other formula that we used, okay? T is still time in years, and k is this constant, and this growth constant or decay constant is going to change from problem to problem. And oftentimes we're going to have to find out and figure out what k is first before we can use it. And we're going to go through that and how to solve that. So again, if you haven't taken a picture of this screen, I would do that, screenshot it, put it in your notes, and then we'll move on. So here's the first. We're just going to go through some problems today. So here's the first example. This obviously is an exponential decay problem. Again, feel free to take a screenshot of this and get it situated in your notes. And then we're going to work through it and try to talk through it in terms of what this all means. You maybe have done problems like this in your science classes, but we're going to work through this one and how to use that formula to help us solve it. So here's what's going on. Half-life. That half-life is basically the amount of time it takes for something to decay to half of its original or current state. And it says that here time it takes for half of the atoms in the substance to disintegrate. So things disintegrate over time. We're talking in this particular problem about carbon-14. So that molecule is going to disintegrate. It's going to take 5,730 years to be half of what it is now. Okay, so we're going to determine the value of k, which means that constant, that rate of decay is what we're going to have to determine for carbon-14. And so we have enough information to do that. We'll find k, and then once we have k, we can actually apply it to other circumstances. And if you hear any of the construction sounds, it's because they're moving trucks and doing stuff to the roof and stuff in the back of the gym. You probably can hear that beeping now, but just FYI, that's what's going on. I'm safe. All right, so here's what you've got to figure out. If A is the initial amount, whatever that is, then Y is the amount that remains after 5,730 years. So its half-life is half of what we start with, half A or 0.5A. So if we start with this, we're trying to figure out the decay constant for when there is half left of what we started. So essentially what we're going to do is set up our formula. So here's our formula. We want to know when there's half of as much as what we started with. We know that it takes 5,730 years to make that half-life occur. And actually, this is all we need. So on this y, we're trying to figure out what the constant is going to be after half of it is left, knowing that we started off with one of it. Okay. The thing that's nice about this situation is I have an a on both sides. I'm actually going to be able to cancel those out. And eventually, what we're going to do is get this k by itself. That's our goal. So my first move is just to cancel out those a's. Okay, since I can divide both sides by a. So I have 0.5 or 1/2 equals e to the negative 5,730k. Now obviously we flip this around to make it look more like a variable that we're used to seeing, like a coefficient. Since I have the e by itself, what do I need to do to get this power down to be a regular number? Hopefully you said take the natural log of both sides, which is what we do. So I take the natural log of both sides. Okay, so the natural log of 0.5 and the natural log of e to the negative 5,730k, and then these basically cancel out. Okay, so I have the natural log of 0.5 equals negative 5,730k. So then all I have to do is divide by this to get k by itself. So I'll do that, divide both sides by negative 5,730, and then I just have to go to my calculator and put that in and see what I get. And I get approximately 0.00012. And you're probably wondering, how many places do you have to go? You want to probably go at least one more decimal point. You want to have at least 2 decimal points beyond the zeros, okay? That way it's not just 0.0001. And for that matter, when we go to use this, if you actually wanted to put this into your calculator when we get to that point, you can do that too, but most of you are going to want to put some type of decimal there, okay? So this is the decay constant, okay? And that's important because for carbon-14, for half-life of carbon-14, we will use K for the rest of the time. And we'll use this K, okay? K, right, got it. So here's our next problem. We're going to apply what we just did in the last problem to come up with the answer for this. So now we're looking at a situation where we've got some animal that contains 2% as much carbon-14 as it would have contained when it was alive. Okay? And so we want to try to figure out how long ago did the animal live. And again, at any time when you're watching this video, if you feel like you need to pause it and reread it and take it in again or rewind it or whatever, please do that. Alright, so we've got our formula now. Okay, so we're using our regular formula, but now we know what K is. Okay, so we're going to use that negative 0.00012 that we came up with in the previous problem. And it's negative because we're talking about decay. All right? And so now we've just got to take the information they've given us and go from there. And we're trying to, how long ago, we're trying to solve for t, is what we're going to do in this particular problem. Okay, so we start off with our formula, and in this case, we want 2% as much. So instead of, like in the last problem, we did 0.5a over here, we're talking about 2%, which is 0.002 of the original amount. Okay, and that's where these two come from. Because it's 2% as much as what they had, it's going to be 0.02 times a. So the good thing here is, still, my a's are going to cancel, and that's kind of what should always happen. Those a's should end up canceling if you've set the left-hand side up correctly, and then it turns into a solving a natural logarithmic equation. Okay. So we'll go ahead and get rid of the a's, cancel them out. Again, I've got the e by itself, so I just have to take the natural log of both sides, which will allow the natural log and e to cancel, which will bring this power down. Okay, and so I get the natural log of 0.02 equals negative 0.0012t. All I need to do is divide both sides by that to get t by itself. Okay, and again, you're going to grab your calculator. And I guess here's the point, where, and I said on the other screen, if you wanted to be super precise, you could put that natural log of 0.5 over 5,730 here instead, so you'd have a fraction and a fraction. I'm not saying you have to do that. You're perfectly welcome to use this. Okay, so here's what the t gives me: approximately 32,600 years. That's how long ago this particular animal would have lived. And so just, again, we've got a word problem. We want to put a bow on it. The animal lived about 32,600 years ago. Make sure we're answering the question, okay? And putting it in a sentence helps us do that. So that's the first type of problem we're going to look at, okay? So that had two pieces to it, really. One, finding the constant k, and then applying that constant to an actual situation. The next type of problem that we're going to look at is going to be a growth problem, okay? So here's an example of a growth problem. And we've got two things that we're going to do in this problem. One, we're going to find k again, similarly to how we did in the other problem, except this is growth instead of decay. and then we're going to try to figure out when Georgia's population will reach 12 million, okay? So here's the problem. In 2007, the population of the state of Georgia was 9.36 million. In 2000, it was only 8.18 million. So obviously in those 7 years, it grew, okay? It grew 1.18 million people, by 1.18 million people. What we're going to try to figure out is if we can predict when Georgia will reach 12 million people. So our process is essentially the same as what we did. It's just a matter of using the growth formula, so the power is positive instead of negative. Everything else remains the same. Now, in order to find K, we have to use both pieces of this information because we know what the population was in 2000. We know what the population was in 2007. So because of that, I can find its growth constant with our formula, okay? And here's why it's set up this way. Sort of starting amount was 2,000. That's the earliest information we have. So my starting amount in 2000 was 8.18 million. And notice we didn't make it actually 8 million. We kept it as 1.18. So long as we're consistent with our units, it's going to work out fine. Because when I eventually I'm going to divide these together. And so whether I wrote 8 million or 9 million or 8 and 9, when you divide those down, it ends up being the same number because the million cancels. So once I've got this set up, it's again, our process is the same, except now I don't have an a to cancel. I have to divide both sides by 8.18 to get the e by itself. And remember, when we're solving exponential equations involving e or logarithmic equations involving e, we have to get the e by itself, and that's what we did in 7.7. Okay, so my first move, I'm going to divide both sides by 8.18 to get the e by itself. Right? Then I'm going to take the natural log of both sides. Notice how I haven't actually divided this out. This is going to give me a more accurate problem, or a more accurate solution. If I divided it out and estimated now, it would be less accurate. So we're going to keep it as a fraction for now. Okay. So then I have the natural log of 9.36 over 8.18, and then the natural log and the e cancel. So I've got the 7k that can come down. Now all I have to do is divide by 7, take all of this, divide it by 7, and I can come up with my constant. All right, and so that's all going in the calculator. And so k is approximately 0.01925. So that's A. I've done that. I found the growth constant, or the rate of growth, whatever you want to call it. All right. And now what I can do is use that constant in this formula to figure out t, which will tell me how long it will take to get to 12 million. So here's the formula we're going to use. Okay. Again, I want to start with 2000. I want to start in 2000 at the beginning spot. That's typically how we want to do this, rather than trying to figure out its growth from here. The growth we started measuring from 2000, so that's why our initial value is going to be 8.18 million. Okay. This obviously is not the initial value in this problem. This is, so that's why we're using it. And then again, 12 million, we're trying to predict how long it will take to get it into 12 million people, get it up to 12 million people. And again, the same idea over here. I didn't write 12 million, I didn't write 8 million. So long as I keep the units the same, the millions are going to cancel anyway, and we're good to go. So why don't you go ahead and try and finish this one up, pause the video, and then come back to it and see if you did it right. All right, hopefully you actually went ahead and did that. My first move is to get the e term by itself, so I have to divide both sides by 8.18. And since I'm not looking for the constant here, I can actually just do that division. That's not a big deal. Then take the natural log of both sides. Again, get that natural log and the e to cancel. So I've got the natural log of 1.467 equals 0.01925t. Divide both sides by that to get t by itself. And t is 19.9, or about 20. We're talking about years again. So what we figure is that it's going to take about 20 years for Georgia to reach 12 million people. Now, it doesn't say how long will it take. It says when will Georgia's population reach 12 million. So 20 years from the starting year, what was the starting year? You should have answered that. Yes, it was 2000. So in 2020, which now is a year away from us, and now I'm curious to what Georgia's population is, so to see if this is even accurate. Give me a second, I'm going to Google it and look it up and tell you. Alright, the best information I can find from the U.S. Census Bureau. The most recent number they have is July 2018, and it is 10,519,475 people. Obviously, that's not 12 million, but it's a couple years away, so they would have to grow by 1.5 million people in the next year and a half, or in the next, from 2 years ago to get there. So it looks like they're going to fall a little bit short of this prediction, but it's not completely inaccurate either. And obviously there's lots of factors that contribute to population growth of a particular area. But this is a good example of how to use some of this exponential growth to help figure this out. Anyway, good luck on your homework. You've got 7.8 day. We're going to spend 2 days on this, so hopefully you'll get plenty of practice and feel good about it. Have a great weekend, and we will see you on Monday.